Okay, we're still on momentum and impulse. Today we'll be looking at Newton's second law expressed in terms of momentum. The first thing that we have to do is to describe Newton's law as you know it from grade 11. Newton's second law as you know it from grade 11. It is described as when a net force is applied on an object of mass m, the object accelerates in the direction of the net force. It accelerates in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass. Let's only focus on the second statement and try to describe it in a mathematical format. The first and most important thing we know is that according to second Newton's law, our net force is equivalent to the product of mass and acceleration. So now that we have this equation, let's look at acceleration, net force, and acceleration, net force, and mass. Acceleration, net force, and mass. Let's make acceleration the subject of the formula in this equation. We will have F net over mass. Okay, this shows that as the acceleration decrease, our net force will also decrease. A decrement in our net force will result in a lower acceleration, and an increment of our mass will result in a lower acceleration. But an increment in our increment in our net force will result in an increment in our acceleration, and will also result in a decrement in our mass. And this whole thing here sums up the relationship between acceleration, net force, and mass. Now that we understand this, let's look at now that we understand the relationship between net force, acceleration, and mass, let's look at acceleration. Equations of motion from grade 10. You know that acceleration is equivalent to change in velocity over time, and this change in velocity over time is equivalent to final velocity minus initial velocity all over time. So let's now substitute acceleration in this second law of motion formula. We will have our net force is equivalent to mass into final velocity subtracting initial velocity over time. So now we will have net force is equivalent to mass by final velocity subtracting initial velocity by mass also, all over time. You will understand why I used a different color for our numerator. Okay, now let's look at momentum. Let's look at the change of momentum. Change of momentum is equivalent to mass by change of velocity, which is just equivalent to mass by final velocity subtracting mass by initial velocity. And if you pay careful attention, if you pay careful attention, this whole term here is similar to our denominator from this equation. So with this, we can conclude that our net force is equivalent to change in momentum all over change in time, or all over time. This means that net force is directly proportional to change in momentum and inversely proportional to time. As change in momentum increases, our net force increases, and as time increases, our net force decrease. So using this formula here, this equation that we have written here, is Newton's second law of motion expressed in terms of momentum, and it is defined in this manner. The Newton's law of motion defined in terms of momentum. The second law of motion described in terms of momentum is the net force acting on an object. The net force acting on an object is equivalent to the rate of change of momentum, of the object in the direction of the net force. If you recall from our previous lesson, when we were talking about collisions, we did mention that a net force, the direction of the change of momentum is the direction of the net force. I did explain that. So the rate of change in momentum, it might confuse you when they say the rate of change in momentum. The rate of change in momentum is just change in momentum all over time. All over time, not all over momentum. All over time. This is just the rate of change of momentum. This is the rate of change of momentum. Okay, let's now look at an example. Associated with this concept that I've just explained now. Okay, here's our example, and let's try to solve it. A bullet of mass 30 grams is fired from a rifle. The bullet leaves the rifle with a speed of 1,200 meters per second, traveling east. The bullet is in the barrel for 0.2 second. Let's read the first question. Calculate the change in momentum of the bullet. Calculate the change in momentum of the bullet. Okay. What is change in momentum? What is our change in momentum? Let's look at it. Change in momentum is equivalent to mass by final velocity subtracting mass by initial velocity. This is the formula to calculate the change in momentum. So let's look at this. What do we have? We do have mass, 30 grams of mass, which will have to be converted to kilograms, because this is physics, we have to deal with kilograms. And we also have 1,200 meters. This 1,200 meters is our final velocity. And then, do we need time for this? No, we do not need time. Time does not play any role in calculating change in momentum. Unless if we were given a force, yes, it would work. But in this case, This is how it is. Now, let's choose east as positive, west as negative, and they are saying this is traveling east. By default, our final velocity will be positive. So to calculate this, we will have, okay, let's convert 30 grams multiplied by 10 to the power negative 3 is equivalent to 0.03 is equivalent to 0.03 kilograms. So now we'll have 0.03 kilograms by 1000 plus 1200 meters per second, subtracting 0.03. And what's our initial velocity? Our initial velocity is 0. That is before the bullet gets fired. The velocity was 0. Immediately it got fired and it left the rifle at a speed of 1200. So this will give us 1200 by 0.036 is just 36. 0 multiplied by 0.03 is just 0. And now we will have 36 kilograms meters per second. East, which is positive for us. And this was the solution for 1.1. This was just the solution for 1.1. 1.2, they say, for 1.2, they say we should calculate the average net force. The average net force, horizontal force acting on the bullet while being fired. Okay, let's store this. Let's store this answer. We have our change in momentum as we have our change in momentum as 36 kilograms meters per second. Okay, now let's attempt the second question. Let's now attempt the second question and see what solution we will get from this. Okay, the average net force, we know that I've just showed you how I've just showed you this formula right now. It's changing momentum all over time. Okay, now let's pay attention. We now have time here, which is 0.02 second, and we also have change in momentum that we have calculated from 1.1. This is a progressive question. Okay, our average net force is equivalent to our change in momentum is it's just 36, and our change in time is 0.02. Oh, this 36 is positive. It's positive 36 because 0.02, and our net force is 1800 newtons where east. 1800 newtons east. 1800 newtons east. This is our 1.2. Okay, now let's look at the last question. They say, what is the average net horizontal force? What is the average net horizontal force acting on the rifle? And explain what is the average net horizontal force acting on the rifle. Explain your answer. Okay, let me explain it like this. The rifle exerts a force on the bullet. And according to third Newton's law, I was talking about collisions. Now, previous lesson it was about collisions, and those collisions were somehow linked to Newton's third law of motion. So, our rifle exerts a force on the bullet, and according to Newton's law, the bullet exerts an equal backward force on the rifle. It's just an equal force of equal magnitude but in a different direction on the rifle. If there are no other forces present, the average net horizontal force on the rifle is 1800. Okay, this average that 1800 newtons east that we have calculated is just a result of the overall force that has occurred in the process. The overall, not the sum, but the overall, the overall average force that has acted on the rifle during the launch of that bullet. In a simple way, I can say that a rifle exerted a force on the bullet. And according to Newton's third law, the bullet exerted a force back to the rifle in the opposite direction, but the force of equal magnitude. So if we assume that there was no other force disturbing these two forces acting, we would simply end up with this force 1800 newtons east. And this concludes our lesson on Newton's second law expressed in terms of momentum.